physicist in the astronomy department here at Caltech, and I will be the host for this evening's event. So thank you all for joining us. Just a couple of announcements, and then we'll launch into our lecture about the shining molecules and atoms across the universe that can reveal the structure of the distribution of matter in the universe, even before the first stars, from our esteemed speaker, Jason Guochao Sun. And so after a couple of announcements, he'll start the presentation. It'll last about 30 minutes or so, and then we'll immediately transition into a Q&A panel consisting of our speaker, Jason, myself, and then two other members of the department, Gina Panopoulou, who is a postdoc who works on a variety of different stuff, but the stuff that I most associate her with is the structure of magnetic fields threaded through star-forming gas and star-forming clouds. We'll also have an exoplanet expert on our Q&A panel, Sarah Blunt, who's a PhD candidate in the department. So it should be a great panel, and we will be fielding questions from all of you. So we're going to do something experimental tonight. We'll have a website that you can go to and ask your questions, and it'll be a bit like a Reddit AMA, where you ask your questions and then you can see other people's questions and upvote the ones that you like. There's no downvoting, unfortunately, but you can upvote the ones that you like, and then we'll pick from the. I mean, we always have lots of questions to answer, and we don't always get to all of them, so we'll pick preferentially the ones that have been upvoted the most. But I'll give you the website to ask those in a little bit. And yeah, and you can ask questions on whatever topic you want related to space and astronomy and astrophysics, and it could be something you read in the news recently and you were like, oh, what's the deal with James Webb? Or, you know, maybe a burning question that you've had for decades that you just want answered by somebody who might have a little bit more background in astronomy and physics. So we will do our best to answer those questions, and we'll go all the way till the end of this 2-hour session, trying to do that. So for reference, we do these events once a month. Our next one will be on a month from tonight, March 4th, being given by Dr. Margaret Lazzarini, who is a new NSF fellow in the department. And she, I believe, is going to be talking about high mass X-ray binaries. These are a massive star and like a neutron star or a black hole that are orbiting around each other, and they pump out tons and tons of X-rays, which should be pretty interesting. And our sister series of events is Astronomy on Tap, that happens again once a month. Our next one, we're actually having one that's totally in Mandarin Chinese that will take place on Friday, February 18th at 7:30 p.m. here, but it'll also be aired in China at that time, which is in the Saturday morning. And it'll be interesting, but it probably won't be very comprehensible if you don't speak Mandarin Chinese. I certainly don't, so I won't be able to understand too much. But for those of us who are Chinese speakers, I encourage you to check it out and tell your friends. Those have been pretty successful. And then our next English language Astronomy on Tap, I think, is a few days after that, maybe the 22nd. And I don't yet know who's going to speak for that, but I'll put all of this up on our website and on our YouTube channel and Facebook and Twitter and all the different social media as soon as I have that done. So without further ado, Jason, would you like to join me? Hello.
Hi, Cameron. Hi, everyone.
Welcome, and thanks for joining us on a Friday night. Do you want to go ahead and share your screen, Jason?
Sure.
Okay. Okay, so Guochao Jason Sun is a finishing PhD student working in the Observational Cosmology Group at Caltech. He has a broad interest in topics at the interface between observational cosmology and theoretical astrophysics, in particular high redshift universe and cosmic reionization. He enjoys reading, cooking, hiking, and building Legos. Oh, sweet. Which Legos have you been working on recently?
I'm working on the space shuttle now, but it's been hanging there for a few weeks already.
Well, I can understand. You've got to finish your when do you defend? You defend in a couple of months, right?
haven't decided yet, but likely sometime this
no
summer.
pressure. Sorry, I'm not trying to. I know how stressful it can be the last year. But, okay, well, sorry for that faux pas there. I'll leave it to you. Thank you for joining us tonight, Jason.
Thank you. Yeah, thanks a lot, everyone. So, hello, everyone. Thanks for joining us tonight. It's my great pleasure today to give you a short lecture about mapping the universe with atoms and molecules that shine. And as you can read from the subtitle here, my lecture today will be a story about how we might stare into some of the uncharted chapters of our cosmic history by mapping the photons emitted from the huge number of atoms and molecules existing in our universe. To give you a quick idea of the storyline, here are the three major themes that will be covered tonight. So I will start with a brief retrospect of how our cosmological views evolve over time since the Renaissance, summarizing some of the key figures, events, and discoveries that shaped our understanding of the universe, in particular, the structure of our universe. And next, I will use the so-called 21 centimeter line emitted by the hydrogen atom as an example to tell you about how modern physical cosmology has been advanced by mapping the universe with atomic emission. And finally, I will briefly introduce the idea of line intensity mapping as a generalization of the cosmological studies using just the 21 centimeter emission, which basically refers to the usage of a much larger set of atomic or molecular emission to map this, to make 3D maps of our universe. Okay, so let's get started. Looking back at the history of what I caught here early cosmology, which refers to the days before the onset of modern cosmology marked by the groundbreaking work of Albert Einstein, we can roughly summarize it by the contribution from these four big names. So stepping through time from what is known as the Copernican Revolution, in 1543, Polish astronomer Nicolaus Copernicus came up with the rationale for heliocentrism in his book On the Revolutions of the Celestial Spheres. So even though it's not a complete betrayal of the aesthetic restrictions of circular motions back in the days of Ptolemy or Aristotle, it sets a great example for human rationality being the true interpreter of the observed phenomena. And the revolution was then followed up by the discovery of laws of planetary motion by Johannes Kepler, based on the observational data from Tycho Brahe. These products of Kepler deeply influenced the philosophy of science in the sense that they set the rule that we still follow today, which is a theory must match the observations within the observational errors. So following Kepler, Galileo Galilei in the 1640s made a number of important findings that provided key evidence for the heliocentric model, including phases of Venus and the moon system of the Jupiter, which completely demolished the cosmological views of Ptolemy or Aristotle. And finally, we have Sir Isaac Newton and his legendary book, Mathematical Principles of Natural Philosophy, whose unparalleled contribution to math and physics don't require any further emphasis. And finally, just wanted to note that you can find these pioneers of early cosmology on the astronomers' monument at Griffith Observatory, which is only about like 30-minute drive from Caltech and featured in many movies like the La La Land. And it's a wonderful place that I strongly recommend to pay a visit if you haven't, when you get the chance to drop by the City of Angels. So then comes another big name, Albert Einstein, who is now considered as the founder of modern physical cosmology. A bit more than 100 years ago, in 1905 and 1915, with theories of special relativity and general relativity, Albert Einstein fundamentally revolutionized the cosmological view since Isaac Newton by inextricably connecting space, time, and gravitation. And as shown by these animations, All of the key predictions of Einstein theory are later on confirmed by observations. For instance, the gravitational deflection of starlight by the sun and the dissipation of energy through the emission of gravitational waves from two neutron stars orbiting each other. And these observations become solid proofs of the success of the theory of relativity. And here on the left, we see a picture taken back in 1931 during Einstein's visit to the Mount Wilson Observatory, which is about 45-minute drive to the north of Caltech. And it is this picture that brings us to the next character of the story, the man standing in the far back, whose remarkable discovery at Mount Wilson once again proved the greatness of Einstein, even though it gave Einstein what he later called his biggest blunder. So that person standing behind Einstein is Edwin Hubble, who is now known as the father of the so-called extragalactic astronomy. Around 1925, using the 100-inch Hooker telescope shown here at Mount Wilson, Hubble discovered probably the most famous observational law in astronomy, which is a linear relation now named after him between the recessional velocity and the distance of galaxies beyond our own Milky Way. It turns out that this simple relation provides a key evidence for the expansion of our universe, an idea Einstein implicitly predicted with his theory of general relativity, but somehow felt uncomfortable with it at the beginning, and therefore made an unnecessary correction for which he later felt regretful and called it his biggest blunder. Nowadays, using the space telescope named after Edwin Hubble, astronomers have already pushed the observational frontier of distant galaxies in the early universe to an astonishing extent. So here, the animation shows you a fly-through of the so-called Hubble Ultra Deep Field, or HUDF, observed by the Hubble Space Telescope about a decade ago. So here, each shiny object is a distant galaxy in our universe, all the way to its childhood. A lot of the photons the telescope detected, and you see here in this animation, were actually emitted more than 12 billion years ago when our universe was still young. So the next important discovery I'll introduce is the so-called cosmic microwave background, or CMB, which is one of the major predictions of the Big Bang theory in the form of relic radiation in the microwave or radio band from the once hot, dense, and opaque universe in its infancy. So in 1964, Arnold Penzias and Robert Wilson from the Bell Lab discovered the CMB signal using a radio antenna shown in this photo. And this discovery turned out to be so important for cosmology, and it won them the Nobel Prize in Physics in 1978. So why is the CMB so important for cosmology? It's quite a complicated story that could be the topic of another dedicated lecture, but the short answer is that precise measurements of the CMB provide rich information about how the universe might have formed and grown since the beginning. So on the right, I show you a visualization of the CMB being mapped over the whole sky by 3 generations of CMB satellites, including COBE, WMAP, and most recently Planck. From this comparison, you can clearly see how the data quality has improved over time. And one interesting thing to note is that even though we see clear color contrast here representing differences in the CMB temperature, the actual difference is super, super tiny, of the order 1 in 100,000. So it's really fascinating to realize that mapping these tiny and hard to detect fluctuations in the CMB signal can actually tell us an epic story about the cosmic evolution. Yet another type of observation that I want to mention is the so-called galaxy surveys. Different from the CMB, which is from and therefore primarily probes the infant universe, galaxy surveys measure the positional information of galaxy distributions in 3-dimensional space of the universe close to the present day. And therefore, as you can see, easily imagine, this provides a straightforward way to map cosmic structures. Here we see an example of the galaxy survey called 2DF. On the left is a visualization of the cosmic volume captured and mapped by the survey, which is denoted by the two fan-shaped things extending from our location in the Milky Way and deep into the space. And on the right is the actual positional data obtained from the 2DF survey, where each of the tiny blue dots represent a single galaxy. As you can clearly see, galaxies are not distributed in a random and uniform pattern in space, but rather there are filamentary structures that were referred to as the cosmic web. Under the influence of gravity, galaxies tend to preferentially form and reside along those like web filament, where the density of matter is higher. And here is just another visualization that you can compare with the fly-through that we just saw for the Hubble Ultra Deep Field. But here we're flying through the cosmic web instead, which is simulated by modern supercomputers. So I'd like to finish this first part of my lecture with a bit of summary and some questions. So here we see a standard picture of cosmic evolution according to our current understanding, starting from the Big Bang on the left to the present day on the right. So as I mentioned, the cosmic microwave background measured by satellite like Planck provides a way to study the universe in its infancy, when it was hot, dense, and opaque. And with space telescopes like Hubble, and excitingly now with JWST, we can study what an adult universe is like by looking at a huge amount of individual galaxies and the pattern of their distribution in three-dimensional space. And it was shown here, thanks to the more powerful JWST as a successor for Hubble, people will actually be able to peek into the teenage years of the universe when the first generations of stars and galaxies appeared. This is for sure a truly exciting picture. However, there are two things to note. So first of all, there are still some missing pieces in this cosmic picture. For example, the so-called cosmic dark ages, which is a period of time after the universe cooled down and became transparent after the Big Bang, but before the time when the nuclear fusion of the first stars ignited and lighted up the universe. So, and also, even though we have powerful observational probes like the CMB and the galaxies, we are only still seeing a tiny fraction of objects in our universe. So the knowledge we have about the early and late universe can be highly incomplete, just like seeing only the tip of the iceberg. So what are the solution and way to proceed here? Well, in the second part of my talk, I'd like to convince you that one viable and actually truly promising solution is the observation of gas. So staring at the night sky or the fancy pictures of galaxies of different looks, we have been used to seeing and learning from the light of stars. However, one important thing to realize is that stars only compose a small fraction of ordinary matter in our universe. A substantial fraction of the universe mass actually exists in the form of diffuse gas, no matter it's inside galaxies or in the vast intergalactic space. So here, to see that, here's a comparison of images of the same galaxies seen through starlight or the eyes of gas. So on the left, we have a commonly seen optical image of galaxy taken by Hubble, whereas in the middle, we have an image of gas distribution, or more specifically, the distribution of neutral hydrogen gas taken by the Very Large Array, or VLA, which is an array of radio telescopes in New Mexico. I won't go into many details here, but from the stacked image on the right, we can easily see that there are clear differences between images of starlight and gas. In particular, the gas image is more widespread and has richer structures. And this is just to show you a quick example of the power and significance of observing not just starlight, but also gas. All right, so if you now agree with me that gas is fantastic, a natural question is then where to find it? And the short answer is gas is everywhere. So for example, gas can be found inside individual galaxies. So as shown in this cartoon, stars inside galaxies form within gas cloud and therefore can still get surrounded by gas once formed. So due to stellar evolution, including the death of massive stars in terms of supernova explosions, some escaping channels can be emptied in the layers of gas surrounding the stars, which will allow starlight to escape from the galaxy into the intergalactic space without being intervened by the gas. And this turns out to have important consequences for the intergalactic space. Because as we can see here from the right, the energetic ultraviolet photons successfully escape from galaxies are able to carve out bubbles of ionized regions in the vast intergalactic space originally permeated by huge amount of neutral hydrogen gas. And over time, as stars keep forming and galaxies evolve, these bubbles will grow in size and start to overlap with each other, and eventually cause a grand phase transition of the so-called intergalactic medium, which start being mostly neutral and ends being mostly ionized. And this process is called cosmic reionization, which is an important topic I'll talk about as an application of neutral gas observations. Okay, so now we have seen why neutral gas is fantastic and where we might find it. Let's talk about how to observe it. Unlike stars, gas is not engines powered by nuclear fusion. So it's pretty much darkness compared with stars, which means observing it will be very challenging. But thankfully, quantum mechanics come to help. It turns out that for atoms of neutral hydrogen, which is the main composition of cosmic gas, there exists a super useful and important quantum transition that gives rise to the emission of photons with a wavelength equal to 21 centimeter. And therefore, we call this transition the 21 centimeter line emission of neutral hydrogen. As indicated in this schematic drawing on the left, this transition comes from a spin flip between two energy states with different spin configurations of the proton and electron of a hydrogen atom. A bit unfortunately, though, the timescale for this transition, and therefore the 21 centimeter emission, to happen is insanely long. One has to wait literally millions of years to see the transition of a single atom. But thankfully, like I said, there are simply so many hydrogen atoms in cosmic gas. So even though this is still a challenging observation to make, especially on cosmological scales, as we'll see, there is still a good chance that it can be detected. So on the left is just an example of the success of 21 centimeter observation, which was used by the Dutch astronomer Jan Oort, the guy after whom the Oort cloud was named, to discover the spiral arm structure of our Milky Way back in the 1950s. So what does 21 centimeter do for cosmology? So it turns out that there are two main regimes of its cosmological applications. So here on the left is an artist's conception of the observable universe, plotted in logarithmic timescale. So we see our solar system at the center, then the Milky Way, then the galaxy outside of the Milky Way, and then the cosmic web, and eventually the CMB as the boundary of observable universe. So for 21 centimeter cosmology, in the relatively late time universe, mapping the 21 centimeter emission can be used as a similar approach to the galaxy redshift survey technique that I mentioned at the beginning. Because as we can see, we've already seen, each galaxy contains a considerable amount of neutral hydrogen. And therefore, the 21 centimeter emission from those neutral hydrogen atoms can be used to trace galaxy positions. On the other hand, in early time universe, or more specifically cosmic reionization and dark ages, the amount of neutral hydrogen inside galaxies is negligible compared with the amount of neutral hydrogen in the vast intergalactic space. So in this regime, the 21 centimeter emission is typically used to map out the structure of neutral gas among galaxies, which is the most important technique so far to study the universe during and before reionization. So here, before I jump into some detailed executions of the 21 centimeter cosmology, I just wanted to quickly remind you the concept of cosmic dark ages and reionization. So simply speaking, these epochs correspond to the time when the first stars and galaxies began to form and eventually formed and caused a grand phase transition of the intergalactic space from being mostly neutral to being mostly ionized. So this process of reionization can be naively visualized as a Swiss cheese, where there are bubbles of ionized gas here and there, whereas the rest remains mostly neutral. And our 21 centimeter signal is just like a sharp knife that allows us to dissect this mysterious chapter of our cosmic history. So now let's look at some a little bit more technical stuff. But don't feel bad if you cannot follow every single detail. I'll be happy to elaborate on these things more carefully during the Q&A session. So, but here, the main idea I'd like to deliver is that mapping how the 21 centimeter signal evolves over cosmic time can give us a whole lot of useful information about cosmic dark ages and reionization. So in the left plot, the top panel shows how the 21 centimeter signal looks like across time and distance. The horizontal axis is the time since the Big Bang increasing towards left, whereas the vertical axis is a measure of the spatial position at a given time. And the color indicates the strands of the 21 centimeter signal, with the blue meaning a positive signal and the yellow meaning a strongly negative signal. The two to bottom panels show the average 21 centimeter signal strand as a function of time and how drastically the signal varies from place to place as a function of time. So the upshot here is that the detailed shape of these curves encode information about lots of interesting astrophysics, such as what's called Lyman alpha coupling, which is a result of the formation of first generations of stars, and what is called X-ray heating, which is associated with the formation of black holes as the first generations of stars died in explosions. And of course, we will learn about the era of reionization from these curves as well. So here on the right, we see one of the most famous and promising 21 centimeter cosmology experiment called HERA, which is located in South Africa for the reason I'll mention shortly. And it is used for detecting the kind of signals shown on the left. And it's impressive to see how these large dishes compare with the size of a person. So to this point, I hope I have convinced you that the whole idea of 21 centimeter cosmology is exciting. However, there is one important challenge to note and to overcome in actual observational data analysis, which is the foreground contamination. So as shown in this left plot, in order to observe the 21 centimeter signal from cosmic dark ages and reionization, astronomers must deal with a series of foreground sources between the signal and the telescope, all of which will contribute to the measured data set at radio frequencies. So these foreground include ionosphere, the emission within our own Milky Way, and also extragalactic sources. And yet another important foreground source is actually the radio signals from telecommunications in our daily life. So altogether, these different sources of foreground add up to a total strength of over 10,000 times stronger than the target 21 centimeter signal, which make the 21 centimeter cosmologist pretty much like the princess who's trying to find the pea. A straightforward solution to reduce the foreground contamination due to human activity is actually to go to the so-called radio quiet zones. And indeed, most of the world-leading 21 centimeter cosmology experiment to date are located in unpopulated radio quiet areas, including those in South Africa and Australia. But of course, astronomers are big dreamers who will not be satisfied by only good observing sight on the Earth. They're also planning on bringing the 21 centimeter cosmology experiment to the moon. So one of such ideas is called FarSight, which is co-led by University of Colorado and Caltech, will deploy antenna arrays for 21 centimeter observations to the far side of the moon to minimize the radio frequency contaminations from the Earth. Whereas the DSL project, led by China and Europe, aims to build a small satellite constellation orbiting the moon to conduct the 21 centimeter observations. So finally, as a closing remark of this second part, I'd like to mention that the 21 centimeter cosmology is not only about reionization. Remember that a lot of neutral hydrogen atoms actually exist inside galaxies. So their 21 centimeter emission can be mapped for the purpose of tracing galaxy positions. This is the idea behind the so-called post-reionization 21 centimeter experiment. And one good example is the CHIME experiment, which aims to use the 21 centimeter signal from the late-time universe to address some of the fundamental open questions in cosmology, such as the nature of dark matter and dark energy. And just as a fun fact, CHIME just reported its first detection of 21 centimeter signal from cosmological distance last night. All right, so in this last part of my lecture today, I'll just I just wanted to take one step further beyond just the 21 centimeter line of neutral hydrogen and tell you a little bit about the general idea of line intensity mapping. With the basic knowledge about the 21 centimeter cosmology in mind, I think it's super easy to understand the idea behind line intensity mapping, which is basically just a generalization of the emission line that gets mapped. So here on the left is a visualization of the production of our cosmic barcode that can be used to conduct line intensity mapping. Whenever an atom or molecule undergoes a proper quantum transition, it will either emit or absorb a photon at a characteristic wavelength or frequency, giving rise to a so-called spectral line emission, emission or absorption. So the 21 centimeter line, in this case, that we have just talked about is just one of many examples. So effectively, these quantum transitions of atoms and molecules create a spectral tags of particles that show up in the observed spectrum of the celestial objects, like a galaxy, as shown here in the bottom right plot, where you can see both emission and absorption lines from atoms of different elements. So a key motivation for extending the idea of 21 centimeter cosmology to the general line intensity mapping idea is to study the complicated gas physics in the interstellar space. So the so-called interstellar medium is mainly composed of gas and dust, and is clearly visible on the left plot of the galactic plane of the Milky Way as it blocks the light from many, many stars. So on the right, we see an illustration of the life cycle of interstellar medium, which basically shows how stars and the interstellar medium interplay and co-evolve with each other. And in red, a number of useful emission lines from atoms and molecules, including neutral and ionized carbon, as well as carbon monoxide, are marked. And these lines are important diagnostics of the interstellar medium physics. And therefore, they have become popular targets for line intensity mapping studies. So in this final slide, I'm just showing you a summary of the general idea of line intensity mapping as a way to map the universe in 3 dimensions and probe the growth of cosmic structures. So compared with the galaxy redshift survey approach that I introduced in the beginning, line intensity mapping measures the aggregate atomic or molecular emission from interstellar or intergalactic gas, without the need of detecting individual galaxies. Therefore, it provides astronomers a more economical way to map the universe. At the same time, using the information about line production contained in the line intensity mapping data, astronomers can learn many useful astrophysics about cosmic gas that is not available from just locating and counting galaxies. Okay, so I think that's all I want to tell you about today. And I think I'll just end my lecture here with one of my favorite quotes from Rachel Feynman, which happened to be particularly suitable for today's topic. And with that, thank you very much for listening. And I look forward to many interesting questions from our audience. Thank you.
Excellent presentation, Jason. Thank you very much. Wonderful. All right, so audience members, we're going to switch to our Q&A panel now, consisting of our speaker, Jason, myself, and two other members of the department who work on other fields of research. Gina and Sarah, would you like to come on? So I posted it in the various different media that we have. We're trying something experimental tonight, rather than just having you type your questions into YouTube comments or Facebook comments or whatnot. I've posted information about another website that you can go to. It's pretty straightforward to use. Go to that website and you can type in your question. And the benefit of that is you can see other people's questions and upvote them, so that we can select the ones that have the most upvotes to answer first. And that might, we don't always have time to ask or to answer all the questions that have been asked of us. So that might make sure that we get the most important ones democratically by all of you. So feel free. I'll put it into the chat again in a moment, but it's a website called menti.com. And then there's a little code that you enter that allows you to see what questions have been asked and ask additional questions. But before we get started, I'd like to have Gina and Sarah, you guys introduce yourselves and what sort of science you work on, and thus what kind of questions you'll be able to answer since you're experts on those fields. So Gina, do you want to start us off, please?
Sure. Hi, everyone. Thanks for joining. I'm Gina Panopoulou. I'm a postdoc here at Caltech. And what I'd like to study is the stuff between stars, what we call the interstellar medium. This is the gas that Jason talked about in the last part of his talk, and it's what makes stars. And the different questions that I'm interested in are, how do stars form from this medium? How does this gas affect the evolution of galaxies? And other interesting things. So I can talk about dust in space and gas in space and questions related to that.
Great. Thank you, Gina. Sarah, you look very cozy in it's like an alpaca jacket. That's wonderful.
My boyfriend's younger brother got this for me for Christmas 2 years ago, and I basically live in it now.
That looks wonderful.
It's very wonderful. It's not real cheap, in case if you were wondering.
That's okay. That's okay. Would you like to introduce yourself and your science?
Sure. So my name's Sarah Blunt. I'm a third-year PhD candidate in the astrophysics department here. And I'm an exoplanet hunter. So that means that I look for and study planets around other stars other than our sun. So I'm particularly interested in gas giant exoplanets, so exoplanets that are similar to Jupiter, but I've studied lots of different types of exoplanets.
Great, thank you. Exoplanets and the interstellar medium, very exciting. And I'm Dr. Cameron Hummels. I am a postdoc here at Caltech. I do computational modeling of galaxy evolution and try and understand the atmospheres of galaxies, the outskirts of the galaxies, and what composes that in terms of both stars, but also importantly and relevant to the presentation tonight, the gas and the plasma material that's there, and how it eventually oftentimes falls into the galaxy and fuels the formation of stars and fuels the interstellar medium, the material that Gina studies. So it's all interconnected. Yeah, so I'm happy to answer questions on, I don't know, a bunch of stuff, but let's see. So there have been a number of questions asked wonderfully in that Menti website. So I'm going to start asking the first ones that have been most upvoted there. And the one that has 6 votes already is: the latest news says that stars are forming around black holes. So do the protostars get eaten by the black hole, or do they only revolve around the black hole? This is a question. There was a press release recently that was in a lot of different news sources. Did you guys see this at all? There's a new AppJ paper that came out about this. So I think what's being referenced here, so just to give everyone context on what I think this question is referencing, generally, we believe that pretty much every galaxy has a supermassive black hole at its center. And when I say supermassive, I mean something, it depends, it's usually related to the overall size and mass of the galaxy that's hosting that central object. So bigger galaxies have more massive black holes, and smaller galaxies have smaller black holes, but they're still pretty massive. The Milky Way has a supermassive black hole that is a few million solar masses. When I mean solar mass, I mean the mass of the sun. So a few million times the mass of the sun. But the black hole that was found a couple of years ago and imaged with the Event Horizon Telescope was, I think, a couple billion solar masses in mass. So it was substantially more massive. And generally these, everyone associates black holes with like tearing things up. In fact, our presentation last month was about tidal disruption events. And when a star gets too close to a black hole, it could get ripped apart, which obviously is bad news for that star. But there was a paper that came out and accompanying press release that indicated that in some systems, dwarf galaxies, less massive than our own Milky Way galaxy by a factor of 10 or 100 or 1,000, in these less massive systems, there are less massive black holes in their centers. And those have kind of a gentler effect on the surrounding medium. And they generate, much like other black holes, they generate outflows of material. So when stuff gets too close, it gets ripped up and it heats up in the accretion flow or in the accretion disk, and that pumps out a ton of radiation and sometimes outflows of material. But in these lower mass galaxies, sometimes that's not quite so powerful, the outflow that flies out. It's a gentler outflow, and that gentle, I mean, it's still going at like 1,000,000 miles an hour, but it's gentler than it would be. And when that bumps into some of the dense clouds of gas nearby or somewhat nearby, rather than shredding those clouds or burning those clouds up, it slams into it and it induces star formation of its own. Essentially, there's a little pressure wave, like a gust of wind that runs into this cloud, and it kind of compresses it a little bit, and it can potentially lead to starting the process by which stars form, which is essentially when gas clouds undergo kind of this runaway collapse due to gravitation. They collapse into really dense little knots and then start nuclear fusion and then create stars. So this can evidently, according to this study, I think it's the first case of this being demonstrated, a central supermassive black hole can induce star formation by this kind of mechanism. But we don't know how widespread it is. This was the first demonstration of that. It definitely needs more study. But I guess the actual question was, do those protostars then fall into the galaxy, or do they orbit around the galaxy? It's dependent on the dynamics of that particular cloud. If that cloud had, I need a demonstration. Here's our black hole. I use my trusty pumpkin and fruit and vegetables. Here we go, grapefruit. So here's we just formed this cloud from this cloud of gas. We formed it into a bunch of stars because of the outflow from this black hole. If they have enough transverse velocity relative to the black hole, they're just going to go into orbit, just like the Earth does around the sun, just like Jupiter does around the sun, like a variety of different gravitational systems. But if there's not enough transverse velocity, then they'll fall in. And that's just an orbital dynamics problem, really. That's much simpler than this compression due to the outflow that's coming from the black hole. So yeah, it all has to do with the dynamics of the system when those stars form, I guess. Do you guys have other things to add on that? Sorry, I just talked forever there about crazy stuff.
was great context. Just to add that, events like a star smashing into a black hole or a planet are pretty rare. So I would guess that it's more likely that it'll just end up, orbiting the black hole than falling in.
Yeah, that seems reasonable. But thank you for the question, audience member. I forget who asked that one. Unfortunately, this doesn't provide me a way of seeing who asks the questions. Okay, the next question that I see here that has 5 upvotes is, what factors determine the star formation rate of galaxies? Okay. Who want? I mean, I don't want to just hog the floor here. Who else wants to talk about star formation rates of galaxies?
I can start and people can chime in. Okay, so definitions first. What is star formation rate of galaxies? So star formation, as Cameron said before, is basically how many stars you form as a galaxy. And the rate is if you divide that with a time. And so what determines how many stars are formed over a given period in a galaxy's lifetime, that is what the question is asking. And there are a number of things that determine that. One of the things is gravity itself. The second thing, that actually gravity is what causes the compression and makes a star. But there are many things that try to push apart the gas that gravity is pulling together. One of those things is called turbulence. It's the same thing that makes eddy-like features in the flow. If you look at a river and where the water falls on a waterfall, it's just making crazy chaotic patterns. That's turbulence in water. We also have turbulence in the gas of the galaxy, and that can dramatically change the star formation rate. It can slow it down, basically. Turbulence is driven, we say, by feedback. So basically stars bursting all over the place. Massive stars tend to have explosive deaths. And so that can cause the turbulence, and that slows down the formation of stars. What other things am I forgetting about, people?
Sorry, I've been trying to manage all the questions here. You're doing a good job. Turbulence, gravitational collapse, the composition of the gas, how much, if the gas is particularly enriched by heavier elements that astronomers call metals, but it's not truly metals, it's just anything heavier than helium or hydrogen. Those tend to be better at cooling and radiating away energy, so it allows the gas to cool more effectively. And when gas cools, it's essentially releasing thermal energy that would otherwise be kind of puffing it up. So it allows it to more effectively collapse under its own gravity and lead to star formation. So usually the composition of the gas plays a role in the star formation rate. But yeah, the fueling, the dynamics, if you have gas that's trundling into these dense environments, or like we talked about just a moment ago, there's pressure waves like from a black hole outflow or from other outflows that run into those clouds, can induce star formation and increase the star formation rate. But I think generally it's mostly just dense gas. If you can build up the density of gas, then you get more stars. And that's why galaxies that existed in the past, when the density of the universe was much higher, that's why, for the most part, that's when the most star formation rate, or the most star formation was going on across the universe in galaxies, much more so than today. It was kind of a nasty place to live, all kinds of star formation going around and radiation from those stars. Not a good place to live.
But yeah, also if you smash galaxies together, that tends to help.
Exactly.
Yeah, just want to add, one of the other highly voted questions actually reminds me something else, which is the magnetic field. Magnetic field can also affect how efficiently stars can form and how efficiently gas can cool.
Indeed, excellent. Good point to make. Good point to make. Okay, looking at the upvoted questions. So relevant to the presentation that you gave, Jason, doesn't the 21 centimeter transition depend on the atom being in a magnetic field? Are there magnetic fields everywhere?
Yeah, that's an interesting question. Actually, I'm not sure if the 21 centimeter emission can be directly affected by the magnetic field, but I can imagine some secondary effect. For example, if the matter itself, like the baryons, what we call like ordinary matter, if the formation of those, or the evolution of structures of those matter, ordinary matter, they can surely, because those matter can carry charges and can therefore be affected by magnetic field. So the 21 centimeter signal will definitely be modulated by changes of baryonic physics. So I could imagine the magnetic field to come into play through this type of secondary effect. But I don't think I'm aware of any like first order or direct impact of the magnetic field on the emission. But I think you're right that the magnetic field is everywhere. It's all over the place in our universe, and it can be important in many circumstances.
So to add to that, there is, as you said, a secondary but very cool effect that happens if you put a hydrogen atom in a magnetic field. The energy levels that you showed are going to split, and instead of having just the upper and lower level, you're going to have 3 upper levels, and that actually produces a polarization of the light. So if you were to put on Polaroid glasses and sort of turn your head one way and the other, or do that for a telescope in some way, then you could actually see the effect of the magnetic field directly on the atomic transitions. That's called the Zeeman effect.
Yeah, excellent. Good old Zeeman. Do we have I mean, I remember learning about the Zeeman effect in undergrad and such. Are there a lot of uses of the Zeeman effect in actual observations of astronomical sources in the optical? Or maybe not the optical, maybe
in
radio.
The optical would be hard.
Okay.
But radio, yes, for sure. That's Zeeman. The Zeeman effect is the main way that we can measure how strong a magnetic field is in the gas of our galaxy.
I think for a couple of stars, this has been directly measured too. Like the Zeeman effect has been used to directly measure the magnetic field in the atmosphere of stars. But I don't know very much about it. I just know that it's a challenging measurement and hasn't been done very often.
Okay. Let's see. The next highest rated question. Is there evidence that the universe has a net neutral charge? And I think there was an accompanying question in the YouTube comments that was something about what would be a way, I forget which method, but what would be a way to determine, like, does light emit differently if it has a positive or a negative charge? Like, would it be possible to see, just based on light, the characteristics of the light? I mean, I guess is this related to our Zeeman question? Like, is there a way of determining if a macroscopic object has net neutral behavior or if it's net positive or net negative? It's a challenging question. Yeah, because generally when I think about it, and we've talked about this before on this, either on Astronomy on Tap or this, in general, you don't expect a lot of macroscopic objects to have a net charge, like to be positive, like substantially positive or substantially negative, because the electromagnetic force works such that if I have my water bottle and I, rub it on my hair or whatever and get rid of, I forget which way it goes. Maybe now my hair is more negatively charged and this is more positively charged. That means it's going to draw negative charges towards it, which are going to intrinsically knock out the positive charge that it has. So it's kind of this self-defeating mechanism that trends towards neutrally charged objects for macroscopic things. But do you guys know of a way that it could be demonstrated that some sort of astrophysical macroscopic object has a net charge? Or do we have a way of, is there any indication, or do we have a way of being able to determine that? I don't know.
I'm thinking, I don't know, maybe a black hole would be a thing that could acquire a positive or negative charge. Just because I remember charge is one of the few things that can describe a black hole.
Yeah.
Yes, but I don't know if in all practical matters, astrophysical black holes can have a charge. And in terms of whether the universe has, a little bit more positive or a little more negative charge, I don't think we can tell because we'd have to, well, in physics, we know the total charge is conserved, right, in a closed system. So whatever charge we started with off in the universe, that's what we have now. But, if there's one more electron than there are protons in the universe, I don't think we could ever measure that.
Yeah, I agree with that. It would be hard.
Something sort of related that I felt like would be fun to mention is that we very often see the process of ionization happening, which is something that Jason talked a lot about in his talk. So this is just where like in astrophysics, you often have situations where something's really, really, really hot, like in the center of a star, for example. And so still the amount of charge is the same, but it's so hot that electrons are not bound to their protons anymore and neutrons. So you get like a plasma or like a sea of nuclei and like sort of free electrons. So we see ionization happening in lots and lots of different scenarios in astrophysics. But that still sort of overall maintains the neutral charge of the object.
Okay, I will move on to another question. For Jason, what do cosmologists most hope to learn from line intensity mapping?
Yeah, that's a superb question. I think the most direct application of intensity mapping to the general study of cosmology, I think it's as a measure of the cosmic structures. So it's you can consider those line emissions as like I mentioned, tracers of matter. So pretty much like how people use galaxies to trace matter. So cosmologists can do a whole bunch of things by mapping the detailed distribution of matter. So for instance, like some of the topics that I briefly mentioned, the nature of dark matter and dark energy, or like different types of dark, for example, different types of dark matter models can have like different predictions on the detailed structures of the cosmic, what we call large scale structures. So by measuring those like detailed distribution of matter, like cosmologists can place like different levels of constraints to confirm or rule out some like different types of dark matter models. And also I think topics like dark energy or some like massive neutrinos or something related to like more related to fundamental physics, like how we use the word like Gaussianity, which means like some statistical properties of the density distribution. So all those like different things may be constrained or those like different models for those different things can be constrained and selected by the data that people obtain from like some measure of the density field. And intensity mapping is just one of the many options.
Sorry, I'm trying to identify these questions, look them over. There's some really complex questions that people have asked, very sophisticated ones. I'm trying to think about the answers to some of them. So another question that's been upvoted, what is the universe predicted to look like in the distant future? I like this. What is our fate? What is our cosmic fate? Do you want to talk about this, Jason, or Gina, or Sarah? I can talk about it a little bit, but I don't want to hog the floor.
It's very bleak and empty. We're measuring an accelerated expansion of the universe. That sounds very scary. Everything is going away from everything else on large scales. On small scales, planets still stick to their stars and stuff, but on large scales, clusters of galaxies, the filaments in the cosmic web that Jason talked about, things are pulling. There's a force that we don't understand, dark energy, that's pulling things apart. And so if the children of our children's children, the very distant descendants of the human race will be very lonely, is what we predict.
One of the story I heard is that like so imagine like super distant future when the wavelength of the photons get like elongated by cosmic expansion, like to like a infinity, that like a lot of the photon will just be like so weak, and you will no longer be able to see them. So you end up being like lonely in that sense, but like except like those like gravitationally bounded system that can survive the expansion.
I can talk about the fate of the solar system too, which is a part of the universe. So eventually our sun is going to become a red giant star. So it's going to puff out its outer layers basically, and it will get so big that it'll envelop Mars. So it won't quite get to the orbit of Earth, but the radiation from the sun will become extremely intense because basically the sun will just be a lot bigger and a lot closer to Earth. So if humanity is still around in 4 billion years or so when this happens, we're probably going to have a bad time. But on the flip side, this is all very depressing. What an awesome time to be living in right now, that the sun is at a regular temperature and there are photons at reasonable wavelengths that we can observe from distant parts of the universe. So there's a flip side too of like, the
magical time to be alive.
Exactly. 4 billion years will be a depressing time to live in 4 billion years from now, but today is pretty cool.
So it's going to go out to the orbit of Venus just before the planet before us.
Yes. What did I say? Did I say Mars? Sorry.
Yeah, I think so.
Yeah. It from what I remember the last time I saw this calculation, it's going to be out beyond Venus, but not quite to Earth. Thanks for correcting me.
Okay. Could the panel members describe some of the research that the James Webb Space Telescope will be performing on interstellar gas? Yeah, what's it going to do on interstellar gas? I don't know any ISM studies that it will be doing. I mean, James Webb is an infrared telescope, so it will be better at looking into denser, more dust-laden regions of galaxies. So it might be able to better study. There are different kinds of galaxies. There's a whole variety of different galaxies. But preferentially in the high redshift universe, there's things called ULIRGs, which is an acronym for ultra luminous infrared galaxies. And these are, we don't well understand them, but they have an enormous amount of gas and dust that's present in them that preferentially absorbs photons in the visible and UV parts of the spectrum and then re-radiates them in the infrared. So it's very difficult to see inside of them using a telescope like Keck or Hubble or something like that. And so you benefit from having telescopes that are able to see at longer wavelengths like those that James Webb will be seeing, but even farther into the infrared to see these systems and to see what they're radiating and potentially to see inside them a little bit and see some of the material in their ISM and in their interstellar media and that sort of thing. So perhaps that's one of the things, but
you can also look at our own galaxy and its ISM, like regions like around massive stars, like H2 regions, so ionized gas, or the dust that surrounds those kinds of regions. So dust in our Milky Way is pretty cold. It emits at the wavelengths that JWST is going to see. So I think people are planning to study our own Milky Way as well. So nearby stuff, not just the very far universe.
Yeah, and just to add to the very far universe, Gina mentioned, like, I think a lot of the optical lines that are what astronomers call optical lines in the rest frame visible light will be redshifted into the proper band of JWST. So like by looking at some of those like rest frame optical lines of metals, people can develop some better ideas of how the chemical evolution of galaxies is happening. So probing some of the like chemical composition of very early galaxies, which is a very important subject of the studies of the interstellar medium.
Sorry, I'm trying to deal with this new interface for seeing all of these questions simultaneously. This is an intrigue. Oh, did you have something you wanted to add, Gina?
No, I just said you're doing great. Keep going.
Oh, thanks. Scientists that Jason mentioned in his presentation had interests not regarded as scientific today. For example, Newton was involved in alchemy and Einstein was in panpsychism. The question is, what non-scientific, in quotes, motivations to explore do you have, if any? Are there things that we're actively looking into that might be regarded as unscientific? I mean, I think that, just to push back on that a little bit, I think at the time, Newton did think that alchemy was scientific. I don't think he was like, oh, I'm going to engage in some weird stuff now that's totally distinct from my real scientific passion of, calculus and gravitation and all of these things. I think he saw it as, and at the time, I think alchemy was somewhat more of a respected, well, certainly more than today, a respected field of inquiry. And so it's kind of a loaded question, because I think if we were, maybe in 100 years or 200 years, we could look back and be like, oh, that thing I was doing, that was totally BS. But right now, I probably think that it's totally legitimate. So it's a little bit hard to identify that, but I don't know I guess I'm going to rephrase that question. Are there anything that are there any topics that we're working on that might be considered fringe? And I'm even saying, like, over the entirety of astrophysics. Not like, Gina, are you doing any fringe science? Or Jason, are you doing any fringe science? But like, we as a field, are there areas of astrophysics that could be considered a little bit more fringy and might not have anything behind them? I mean, science is constantly correcting itself. Like 100 years ago, there was the prospect of the ether, the ether that permeated the universe, and was justified because we saw electromagnetic waves traveling towards us, and so thus there had to be an ether, a medium through which those waves were traveling. And now we understand that electromagnetic waves are self-propagating and they can exist in the absence of some sort of medium. But at the time, that was a popular thing to think about. So what do you guys think? Are there fringe areas that might not be as science?
So I can go on a sort of related rant, which
Sure.
is that I think astronomy is different from some other scientific disciplines, not all, but some, in that it's primarily exploration based. Like, we're not always following the scientific method rigorously, in that we're not always like saying, here's a hypothesis, I'm going to go out and test this. Sometimes we do that, but sometimes we're just looking. We're just like trying to make a new type of measurement, or look in a new location, or look farther, or look smaller, or something. And because of that, a lot of times we're not trying to many times we're not trying to prove a theory. So I think it's, in that spirit, it's sort of harder to be fringe, because if you don't know what you're looking for, you sort of expect anything. That said, I think there are questions that no, I'll stop there. That's my rant.
So
Yeah,
I can add. Oh, go ahead.
Sorry, go ahead.
We started at the same point in time.
Okay. I just wanted to add two words. I think maybe can add to what Sarah said. It's just the difference between first principles and empiricism. I think that's something astronomers should be thinking about, when they're doing research, trying to know the difference and what are the pros and cons. That's my thought.
Cool. And what I wanted to add is, so I'm reading a book that Chandrasekhar wrote. This is a very famous astrophysicist, and it's called Truth and Beauty in Science, or something like that. I'll try to find the title and say it explicitly. But so he examines the motivation to do specific kinds of research that stems from appreciating beauty, and that can be considered pretty fringe. But I find the book very interesting because he sort of starts off very young and says, beauty has nothing to do with why we want to do science. And then as he ages, these are essays or talks that he gave in the book, he sort of changes gears and goes into, beauty is a way that we can use to appreciate science. And it's also, a way that helps us find sometimes the correct theories. For example, theories that have symmetry are considered beautiful. So that's what came to mind.
I don't know. I'm having a hard time thinking of things that could be considered fringe without just offending a huge portion of the astronomical community by saying that their work is fringe or is just speculatory. I don't know. Maybe I should just bite the bullet and say it, but yeah. But I mean, the problem is we don't know, right? In 100 years, it could be seen that this an area so for instance, there's a huge number of scientists who go into the field of string theory to try and understand the unifying theory that unifies all of these different seemingly disparate forces, the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity, right? And then potentially now we've got like dark energy and such that throws things into it. And it would be nice to have one all-encompassing theory that we can describe all of these different disparate behaviors. And string theory and related theories are attempts at doing that. And, you know, the problem is at this level, there aren't any real predictions made by those theories. So oftentimes it's right on the edge of what's considered science, because science makes testable predictions. So you can test to make sure that your hypothesis is correct or incorrect. And at this point, we haven't reached a level, and I don't think it's for lack of trying. I think it's just a very, very, very difficult problem to address. And we haven't reached a stage where those are making testable hypotheses. And so I wouldn't say it's fringe. It's just, it's hard. It's hard to do. And many of those things are probably by necessity going in totally wrong directions. Does that mean they're not worth doing? No, because I think basic research and even stuff like that can just reveal new insight into other problems. But yeah, that's kind of the example that jumps to my mind. But I wouldn't put it in the same category as alchemy or panpsychism. So I don't really know. We don't know till all the cards are played and we can see in 100 years and look back and be like, of course, those people had it all right, and those people over there were a bunch of dummies. So, you know, it's hard to know. Sorry, I don't have a good answer for that one. I encourage people to ask questions in the Menti link. People are continuing to do so, but I know there's a lot of questions that are being asked in the chat as well. And it's hard for me to like move all of them back to the Menti and vote on them and everything at the same time. So I'll just keep on looking at the Menti stuff and trying to address the questions there. Here is a question that's been upvoted a few times. Is the universe infinite? Is the universe infinite? Jason, you talked a little bit about this with respect to the observable universe and such, but it's a question that oftentimes we get in this sort of thing. So do you want to take this, or does anyone else want to take this?
I can start by saying that the observable universe is not infinite, and it existed for like a limited amount of time. So that's the something we know. But beyond that, it kind of depends on the cosmological model that is valid, and which we have some evidence for the shape or the how exactly our universe is like at this point, but there are still pretty much controversial. So it's whether the whole universe is infinite or not. I think it's a rather deep question that sort of depends. Yeah.
Yeah, I agree with that. I mean, at some level, we can't really answer it because, yeah, we have our observable component of the universe, and that's dictated by the fact that the universe had like a finite beginning, which I think most people agree is the case based on the Big Bang theory of cosmology. But yeah, beyond that edge, it's hard to say, right? It's hard to say if it goes on forever or it doesn't. So it's kind of a way that we can sneak out of answering. So I'll sneak out of answering that because we can't really speak to things that are outside of our way, our collection of data beyond that edge.
But I thought that the standard model of cosmology requires an infinite universe. Well, requires that's what is consistent with
Lambda CDM?
Yeah. No?
I don't think so.
Okay.
I don't know. I can double check, but I don't think that's true.
I'm curious now.
Okay. I'll let you dive deep here while I keep going through questions, and we can revisit it in a few minutes. All right. Next question, most highly ranked. Why are the dispersion measurements from fast radio bursts only affected by free electrons and not other particles? Oh, you guys are pulling out the good questions here. Okay, so basically let's talk about context first. For those of you unaware, we've had a couple of talks about fast radio bursts. We had one by Liam Connor in December for our stargazing lecture. So if you're interested in learning more, I encourage you to check it out. He did a very good explanation of this whole phenomenon. Fast radio bursts are a recently detected phenomena in the last 10, 15 years, where we see short-lived bursts over the course of a few milliseconds that are coming from distant objects in the sky. So it's like a flash that we see for a very short period, and we see it in the radio part of the spectrum, but no other parts of the electromagnetic spectrum. We don't see them in light, like visible light. We don't see it in UV. We don't see it in gamma rays. We just see a flash of radio waves. And we can tell there's something called dispersion measure, which is, it causes a dispersion in that radio frequency burst that's coming at us, such that the higher frequency wavelength or higher frequency photons arrive faster. They arrive sooner to us than the slower. I think it's that direction. It should be that direction than the lower frequency photons, and that's called dispersion. And what causes that dispersion is the presence of free electrons along the line of sight from where that burst was emitted and us when we eventually receive it. And it causes this dispersive effect in the radiation that goes through it. The reason it's the free electrons and not other particles, it has to be a medium that has charged particles along that line of sight. So they could be, it also works with protons or bare nuclei. Any kind of ion will cause this effect. But I believe that it is tied to not just the charge of the particles, but the mass of the particles. And because the electrons are the lowest mass of the particles that are charged particles that are going to be found throughout most of the universe, they're the ones who create the bulk of the signal that causes this dispersive effect. But in terms of the details of why you get dispersion from an astrophysical plasma, that's too much to do right now which is basically just revealing that I don't understand it as well as I should in order to be able to explain it. But perhaps one of the other panelists better understands it so that they could explain this.
I think I also don't understand this very well, but the sort of useful thing that I keep in my head is that at the basic physical level, you need a wave to propagate through material, and the wave propagates via charged particles like vibrating back and forth. So the EM radiation is jiggling these particles, and electrons are less massive, so they're easier to jiggle. So that keeps the wave propagating more easily. So like Cameron said, this could also happen with protons or any charged particle, but it's much easier to see when electrons are doing it, and it's much easier for the wave to keep propagating.
Good explanation. I like that. Okay. The next question that's been upvoted: cosmic microwave background radiation, much like what was discussed in Jason's presentation, is radiation from when the universe was only 380,000 years old, much younger than it is today. Why was there no radiation from before that period, earlier than 380,000 years? The universe was hotter then, and hot bodies should emit more radiation. So why is there no radiation from before 380,000 years after the Big Bang, after the birth of the universe? I can yap again, but I don't want to hog the mic. But if people want me to, I'll do it. Yeah. Okay. So in the early universe, I need another model. Here's my grapefruit. In the early universe, when everything was, as the person who asked the question is quite correct. When you start with the very earliest universe, just after the Big Bang, everything, all the mass and energy of the universe is crammed together much, much more densely than it is today. I'm going to represent this as a sphere. It's not necessarily accurate because we talked about the extent of the universe could be infinite. This is just meant to be that it's a very dense medium where you've got matter composed of mostly protons and electrons around this period of, we'll say, 200,000 years after the Big Bang. Earlier than that, and things were even so hot that you didn't have protons and electrons. It was more quarks and things. It was even smaller, more fundamental particles. But we'll say we get to like 200,000 years after the Big Bang, and you've got a bunch of protons and electrons flying around in this soup. And when a proton gets close enough to an electron, it might form together into a hydrogen atom. That's what makes a hydrogen atom, right? Is a proton and electron. So it might form into a hydrogen atom, but also present in this soup of everything that's flying around in the early universe are photons. And they're very energetic photons because it's dense and the energy density is very high. And the energy density is so high that those photons are quite short. They're UV or X-ray photons. And as soon as that hydrogen atom forms from that proton and electron that get close enough to each other, a photon slams into it and it ionizes it. And it knocks that electron off of the proton. And then you don't have that hydrogen atom anymore. The thing that's special about that 380,000 year number is that, remember, the universe is expanding. So each year it gets a little bit less dense, and your matter density stuff isn't as close together, and the photons are also stretched, so they aren't as energetic. And finally, what happens at 380,000 years is that the wavelength of the photons becomes stretched enough that it no longer has enough energy when it slams into that hydrogen atom to ionize it anymore. And so essentially what you had before 380,000 years was that your matter field and your radiation field were coupled together, and a photon had just run into an atom and get absorbed. And so atoms were just constantly being formed and then ionized and formed and ionized. And finally, at 380,000 years, the photons became stretched enough that they weren't energetic enough to ionize those atoms anymore, and they just started free streaming. And then you had the atoms that were like, okay, now we can finally chill out instead of getting knocked around by these energetic photons all the time. And you had the first essentially neutral hydrogen that could form consistently and remain in neutral form for maybe the rest of the age of the universe, unless they formed into stars or something like that, or got slammed by reionization. But that was later. So the thing that's special about 380,000 years is just that's when the energy density of the universe stretched enough and got low enough that you finally allowed photons to stream. And when we're seeing the cosmic microwave background photons, those photons are left over from that kind of moment. It wasn't necessarily it wasn't like a phase transition that happened instantaneously, but roughly at that time, that's when that happened. And so we're seeing the photons that now have continued to stretch over the 14 billion years since that time. And instead of being Lyman limit photons at 912 angstroms, they've stretched out to being cosmic microwave background photons that are, what's the wavelength of CMB photons? It's like a centimeter or something, or millimeter. I don't know. I think it's millimeter. Something in that scale instead of something in really small scales. So yeah, that's why we don't have radiation from before then, because all the radiation was just bumping into stuff, and we can't trace it back through that maze of material prior to that time. I hope that.
Yeah, and just to add, I think this question is in some sense related to the previous one, because we are, in both cases, we have the Thomson scattering of free electrons, which contribute both to the distance measure and
that's a very good, yeah, that's a good
and the opacity of CNB. Yeah.
That's a very good point, that it totally relates to the previous question about the dispersion measure and free electrons. Yes. Yeah, so that was a great question. I hope I didn't butcher the response and it made some sense. Oh, goodness. Oh, I don't know how to answer this question. We say that a photon has no time, but how does redshift vary with time? Or is time a property of mass? Oh. Okay, so I think the reference is, we say photon has no time. I think what the asker of that question is implying is, from the reference frame of the photon, the light ray, it's traveling at the speed of light. And so for it traveling at the speed of light from, this place in the universe or that place in the universe to here, it's effectively not experiencing a change in time because it's traveling at the speed of light. And it's the whole like relativistic time dilation. The faster I'm traveling relative to some fixed frame, the less I experience time relative to that. Did I get it right? Did I go the wrong way? Yeah, that's right. The less I experience time relative to that fixed frame. But the rest of this question, but how does redshift vary with time, or is time a property of mass?
So I feel like I have a thought. I don't know if this is exactly what the question asker was asking, but this is something, I'm just going to explain something that I was confused about when I got to grad school and took me taking a cosmology course to sort of finally understand. So there are a couple, so redshift fundamentally happens to a photon because an object is moving away from you. So if there's a planet which is relatively, or a star that's relatively nearby to us on a cosmic scale, is just moving away from us, we would see it redshifted. Another thing that's happening on top of that is the universe expanding. So that means that if you look at things that are farther away, they're going to be moving away from you. So things that are farther away generally have redshift just because they're moving away. There's another effect that's happening, which is just that things that are farther away happened earlier in time, and that's related to the finite speed of light. So since light takes a while to get to you, the things that you're looking at that are very far away, actually, like, that light was emitted a while ago. So that's why when we look at the cosmic microwave background, which is 13.6 billion light years away from us, that's the farthest back in time that we can see, because it's so far away that the light has been traveling for 14 billion years to get to us. So this means that we can use redshift of really far away things to tell A, their distance, and B, how long ago like what time in the universe we're looking at. So it's not that redshift automatically implies time. It's that because we know the universe is expanding, we can use redshift to figure out how fast something is moving away from you if it's really far away, and B, what that means for when it formed, or like what time in the universe we're looking at and what distance away we're looking at. So it's a lot of sort of things to keep in mind, but that's sort of something that astronomers will confuddle, that's not a word, but confuddle a lot. Like redshift in general is just a property of anything, and then like cosmic redshift that's related to the expansion of the universe. I have no idea if that answered the question, but there you go. Now you know about redshift.
Yeah, it's hard. It's a hard question to address, but exactly, it's related to the farther you get. I don't think that time. I think the question referred to time being a property of mass. I think it's related because mass affects the distribution of space-time, and time is obviously tied to space-time. And so there's a relativistic effect where you're closer to a massive object. And so your tendency to move forward through space-time is modified by the presence of that mass distribution. So in some ways that's correct, but I'm having trouble coming up with like an all-encompassing response to that.
So I didn't talk about gravitational redshift at all, but like Cameron said, this is a third thing that causes redshift. So I talked about just like velocity, just motion causing redshift. There's also this cosmological redshift, which we observe things that are farther away in time and distance moving away from us, so we can predict their redshift. And then there's a third general relativistic prediction that things that are heavier will it'll be harder for photons to escape from them. So that also photons will sort of be slower, not exactly, but sort of that's what's happening, is that photons will be slower in escaping from really massive objects. So that's a third type of redshift, and that is related to mass. So when you measure a redshift for an object, it's actually the sum of all of these effects. It's the local velocity of this object, also the cosmological redshift, also the gravitational redshift.
Yeah, that's great. Did I mess up the photon experiencing time? Gina, did I mess it up? I may have messed it up.
Yeah, I think just to remind myself, the equation for time dilation is if you're a moving observer, your time is stretched with respect to a non-moving observer. And so a photon that goes at maximum speed is going to experience time as infinite. I don't know what that means, but as time grows because of this relativistic effect, because of the motion of the photon or an observer, space shrinks. And so you get basically a photon does not experience distance at all. Everything is where it is.
Because
I don't know
along the line of propagation, it shrinks, and so it gets there. There seems to be a bit of an echo with your microphone. I think you can mute the YouTube or something. I'm not sure. Anyway, the next question that's been upvoted: are there any examples of X-rays or other high-frequency photons that have been redshifted into the visible part of the spectrum? Whoa, that would be quite a long redshift to go from an X-ray photon that, let's say, is at 10 nanometers to something in the optical, which is at 1,000 nanometers. So that would be a redshift of something on the order of 100 times.
1,000 nanometers, Cameron. You are definitely not an optical astronomer.
Well, I didn't want to use angstroms. I think in angstroms, but I didn't want to use angstroms because that's such a weird unit that is just, I don't know.
No, you're right. Order of magnitude is fine. It's funny.
People aside from astronomers don't think in angstroms, I think, even though I do. But the point is, there has to be, that's a redshift factor of something like 100, or on the order of 50 or 100. And I don't think that we have any demonstrations of this sort of thing, certainly not from cosmological redshifts. So cosmological redshifts, as we've been discussing, describe the farther away in the universe something is, the more the space between us and that object has expanded. And so the faster it's traveling away from us. And so the Hubble Space Telescope or the James Webb Space Telescope hopefully will be able to achieve detecting objects at kind of the very distant edges of our observable universe, which puts things at something like redshifts of 10 or 15. We think the first stars were forming at redshifts of 30 or 40. I think the cosmic microwave background is at a redshift of 1200. It's like something, I guess that's the only example that I can think of something that's been stretched quite so far. But I don't think that we have examples of X-ray sources that have been stretched all the way to the optical, meaning that it would be a redshift of 100 for a variety of reasons. Just one, I think, is that if you have an X-ray source that's that far away, the X-ray photons are going to get stretched to the point where they're in the ultraviolet part of the spectrum, and then they're going to get absorbed by neutral hydrogen that's in the way, much like Jason was describing during the cosmic dark ages, where there's just a bunch of neutral hydrogen sitting there. It's going to absorb those X-ray or UV photons when it travels through it, and they're never going to make it to us. It's like there's going to be a big curtain in the way. And I can't think of, like, maybe deep down the barrel of a black hole, you could experience gravitational redshifts on par that might be like that, but I don't know. I don't think it's been demonstrated that we have anything that's quite so redshifted. Do you guys know? Yeah. But very good question. I mean, insightful.
Yeah, just because we don't know of anything doesn't mean it hasn't been done. So there might be something out there. I don't know.
Indeed. We only have like 20 minutes left. All the remaining questions, like if you really like your question, I encourage people to go onto that Menti website that it should be up in your, I've posted it a couple of times in the YouTube comments. I posted it a couple of times in the Facebook comments. And I encourage people to go there. Even if you don't have a question, you can look at the existing questions that have been put there and you can upvote them, because all the remaining questions have between 0 and 2 votes. So it's not like a strong consensus on which ones we should do. Maybe I'm just going to pick out the crazy ones, the interesting ones that we should try and, here's a good one. Kind of it extends over multiple Menti questions because there's a character limit. We've been looking for dark matter for a long time now, and we haven't found anything. We haven't found any like direct detection of dark matter, I think is what they mean. But sure, we haven't found anything yet. There are a few people who suggest that there are no such dark matter particles, that instead we need to change our theory. At what point do we say, if any, at what point do we say, well, maybe we shouldn't build a bigger experiment. Let's think harder in changing the theory. That's an excellent question. And people have been proposing this. I think sometimes it gets confused. Like in some things in science, there is a grand consensus amongst scientists that something is, everyone agrees, and maybe there's a few fringe people who disagree with something. And then in other areas, there's a lot of turmoil. And for a long time, with the prediction or the theory of Big Bang cosmology and the presence of dark matter, there was a lot of, and there's still pushback, as the question asker says, that clearly we don't fully understand dark matter. We haven't yet detected it. There is a decent number of people who for a long time proposed an idea called MOND, modified Newtonian dynamics, which was a way of getting some of the impact of the presence of dark matter without having to invoke some sort of invisible particle that magically interacts gravitationally but doesn't interact through other means. But MOND is kind of disfavored. I'd say it's really disfavored these days. There have been a number of different experiments that have been done to kind of show that it can't really work in that way. But MOND was a way of modifying, I'm sorry, I didn't explain that, modifying the laws of gravity as we understand it to have an additional term that effectively takes care of this additional force that we see on large scales. Like galaxies tend to show additional mass that we invoke as dark matter. But MOND was a way of addressing that additional force, instead of invoking that there was some unseen matter, that there was just some very small term in the gravitational equations that only showed up on large scales on par with galaxies. But we've since kind of disproved that. The bullet cluster was a very good example of this. I don't want to get into the details of that because I'm already rambling too much, but I encourage people to look up MOND and bullet cluster in Google, and you can find out more about why the bullet cluster in many ways kind of was the bullet's kind of appropriate because it was the bullet that kind of ended the MOND theory. But people are, this is a concern. Like, dark matter holds together well for the most popular version that seems to explain the evolution of the universe, which is lambda. It's called lambda CDM, lambda cold dark matter universe. Lambda being dark energy and the expansion of the universe, the accelerating expansion of the universe, and CDM being cold dark matter for explaining how galaxies and larger structures hold themselves together due to gravitational effects. And it might not be right. There might be problems with it. But yeah, I don't know. It's an open question. And people are looking into this. People are trying to find dark matter, but there's a huge range of different energies and mass scales at which dark matter could exist. And yeah, it could be a technological problem, or it could be it could be that we're down the wrong path. But at least from the evidence that we see so far, dark matter is the most favored thing. Sorry, what do you guys want to say? I'm just sitting here yammering.
Yeah, it could be the modern version of either, but hopefully that's not the case.
The modern version of
either.
Of ether. Yeah, it could. Yeah, it could indeed.
I can also talk about an alternate dark matter theory that has been mostly disproved, which is so when dark matter was first discovered, or when we first found evidence that there was something that was making galaxies behave weirdly that could be explained as just extra mass that we couldn't see. People initially thought that this mass could be explained as cold stars and planets. So basically, like, just so this is called, so the current like dark matter theory is called the WIMP theory, or the weakly interacting massive particle theory. And this alternate explanation was the MACHOs. MACHO is, what is MACHO? It's
massive compact halo object.
Thank you. Massive compact halo object. So if you have something that is not very bright, but has a lot of mass, and there's just a lot of them. So basically, if you just had like a ton of free floating planets in the galaxies and you just couldn't see them because they're not very bright, then that could sort of explain this away as well. The problem with this is that there are other ways that we would be able to detect these MACHO objects. In particular, there's a method called microlensing, which is where planets or other objects come into chance alignment with a background object. So say I'm observing a star from Earth, and this star is very far away, and then a planet like passes in front of it. It makes the star's brightness increase very rapidly, and that's due to general relativistic effects. So the sort of nail in the coffin for this MACHO theory of dark matter was that if there were so many free-floating planets that we couldn't see, we would be microlensing. The microlensing rates for these planets would be off the chart. So, and the fact that we don't see them, that microlensing rates for planets are not crazy, means that there's not enough planets or small stars in the halos of these galaxies in order to explain this difference. So I guess all that to say that, like, people are actively investigating other theories of dark matter, but nothing's worked as well as this weakly interacting massive particle, or lambda CDM. But we're all ears. We have ideas.
I will move on. All right, moving up. Just moved up, got upvoted. Our reality is in 3 dimensions. However, is it possible that the universe expands in higher dimensions?
I love this question.
Yeah, that's possible. Do you want to take it, Sarah?
Yeah, sure. I love talking about dimensionality. So, I talk about this with my brother a lot. I'm really boring, and I'm gonna make the boring claim that dimension is just a mathematical way to understand the universe. So you can describe something, you can define dimensions any way you want. It's convenient for us to say that there are 3 spatial dimensions because you can describe any point in space with a combination of those 3 spatial directions, like, up and down, left and right, and north and south, and east and west. So you can describe any point in 3-dimensional space in those with coordinates in those 3 dimensions. But you don't have to describe it in 3 dimensions. You could say, like, I'm going to also add in an element of time. So, like, if I'm walking around, I might be in this location at one time, but if I want to know exactly where I am in 4 minutes, that's a different, I'm going to use the additional dimension of time in order to describe this system. So when people say, like, could the universe be more than 3 dimensions? It absolutely could. And it's just a matter of definition. It's just a matter of how we define the way that we're describing things in the universe. Yeah. So I think usually when people ask this question, like, they're thinking about, okay, did anyone ever, when I was in elementary school, we watched this video called Flatland. I don't know if anyone ever saw it, but it was an amazing video. And basically the concept behind this video was that there were these little, like, flat dudes that lived in 2-dimensional space. So they just, like, went around the world in their little 2-dimensional plane. And then all of a sudden one day, I forget what this character's name was, but there was this character who was like Mr. 3D or something. And this character lived in 3 dimensions and just moved around the space. And people were like, this is so weird. Like, we can't understand how this guy is doing all these crazy things. And then they realized that, like, if you invoke this other dimension, that they can't see, that they can't perceive, it all of a sudden explains this mysterious character's motions. And so that's sort of what people are saying, like when they say, like, Einstein proposed the 4th dimension of space-time. It's not necessarily that there's some, like, mystical other, like, plane that we can't perceive. It's just that it's some other way. It's some other, like, it's an additional, like, constraint that helps us to understand the way that physics works, basically. So Einstein said, okay, there's this 4th thing that if we include that as an additional constraint, it allows us to understand how orbits in particular work. Okay, so there's my rant about dimensionality.
Oh, that's great. And to be honest, so I haven't seen the film that you mentioned, but there is a book as well called Flatland that was written, like, in the late 19th century. And it's one of my favorite books. Like, it's this whole same idea. There's some weird, like, Victorian societal norm stuff that's mixed in there, like women being subservient and so on and so forth. That's a little bit weird, but product of its time, I suppose. But the whole idea of all the characters existing in this 2-dimension, they're like triangles and squares walking around in their 2-dimensional space, and then they interact with a third dimensional being, and it's like basically doing magic. And so it's a really good analog for us as 3-dimensional beings to think about what a 4-dimensional being or a 5th-dimensional being might be capable of doing and interacting with us. It's a real interesting book, and it's a short story, so I encourage people to check it out. But yeah, there's some weird Victorian stuff in there. But
yeah, I guess another way you can think about, I'm very interested in this random subtopic, but another way I like to think about it is, like, so say that you were trying to understand humans by only looking at their shadows. Like, this is basically a perfect analog of, like, trying to understand a universe that has some additional dimension that you can't perceive. Like, you look at a shadow and it has a lot of the same characteristics as the 3-dimensional thing, but you can't really, like, completely describe the thing. There's some information that's going to be lost to you because you're moving from an actual three-dimensional thing to a two-dimensional projection or representation of it. So, yeah. So you can kind of think about it like that. If there's some additional physics that's causing the universe to have some structure in higher dimensions, and we're only seeing the projection of it in our however we're choosing to describe in our 3 dimensions, then there might be behavior that is weird that you might not understand.
True. We are coming up on the end of the evening. There's one more question that I'm actually interested. Well, there's two. There's one that's a joke question about the Outback Steakhouse in the Maldives that's referencing something that we did in Astronomy on Tap like 6 months ago. So thank you, whoever posted that. That always makes me smile and chuckle. Of course, there'd be a fine restaurant like the Outback Steakhouse in such a luxury rich place as the Maldives. But the question that I was interested in is, how do we differentiate cosmic microwave background from other microwave and radio waves that we see in the sky that are from other astrophysical sources than this kind of light echo of the Big Bang? That's a good question. What do you guys want to handle this?
Sure. It's very close to what I do. So
excellent. Right.
So it's very fortunate that the universe started in a Big Bang, and basically the cosmic microwave background is just like a cooling down furnace or an oven. So if you look at different wavelengths around the frequency that around the wavelength where we detect the cosmic microwave background, you're going to see, I'm going to plot something with my hands. So on the y-axis, I'm having how bright the cosmic microwave background is, and on the x-axis, we'll have different wavelengths or different colors. And so what you'll see for the cosmic microwave background is that it does something like this. And these are logarithmic axes, but never mind. So the cosmic microwave background is a perfect black body. That's what we say. It's what you expect a perfect oven to do, basically. But all the other things that emitted microwave frequencies, like dust in our galaxy or cosmic ray electrons in our galaxy, all those other things have a totally different spectral signature, right? If you were to look at dust emission from our galaxy on its own, it will have a shape that's sort of like this, very, very different from the cosmic microwave background that I drew. Synchrotron emission, on the other hand, just goes like a parallel, like this. And so by understanding the physical processes that create these microwaves, we know the spectral signatures to expect, and we model all of the emissions as a function of wavelength, and that's how we can extract each of these contributions. That's how we separate the cosmic microwave background from all of the other stuff.
Great. Well, I learned something. So, all right, that takes us kind of to the end of our time tonight. I would like to thank all of the panelists, Sarah, Gina, but especially Jason. Thank you for your presentation tonight. That was really excellently done. The slides in particular were just like visual gems. I'm going to have to mine that in future presentations that I give. And thanks to our audience members for tuning in on a Friday night when clearly you have lots of options on how you can spend your Friday night. So it was a pleasure to interact. If people in their respective streaming services can give something in the comments about how much they liked or disliked the menti.com interface for doing the Q&A. I know it's an extra step to go to an additional website. You can go to a website on your phone, you can go to the website on your computer, but to ask the questions there, is that beneficial? I like the fact that you can upvote other people's questions. So rather than me just randomly selecting the questions that I think are the most interesting, we're actually getting the ones that you guys really want to have answered, that are the most upvoted, which sometimes it makes it challenging for us because those are the hard ones. And you could definitely tell that I was stumbling through a few of those because I don't necessarily know the answer to all the things. I'm no Alex Trebek. So, but yeah, let us know in the chat if you appreciated that or don't, and we'll maybe use it again in the future. So, some parting comments. Our next event is an astronomy on tap entirely in Mandarin Chinese on February 18th, two Fridays from today. Our next astronomy on tap in English is 3 days later on Monday, the 21st. I'm not sure. I think one of the speakers will be talking about gravitational waves from merging black holes, which should be interesting. I'm not sure what the other speaker is going to talk about. And then our next lecture like this with followed by Q&A will be a month from today on March 4th, given by postdoc Margaret Lazzarini in the department. She, I believe, is going to talk about high mass X-ray binaries. So a massive star next to like a neutron star orbiting around each other, and there's an interaction that causes like copious amounts of X-rays and high energy photons that are radiated out. They're some of the brightest X-ray sources in the sky. So that should be pretty interesting. And I think that's all I got. So, one last thing. At the end of the month, if you live in California, we will be helping out at an event called the Death Valley National Park Dark Sky Festival. This is open to all. It's free. You can go to Death Valley. I mean, you can go from anywhere, but I'm just mentioning this for people who live in California because it's, you know, it's only a few hours drive. You can go and there will be a star party with telescopes set up. There will be lectures from scientists, some scientists from Caltech, some scientists from JPL. There will be representatives from the James Webb Space Telescope team giving some lectures. There will be tours of different locations in Death Valley that are similar to conditions on other planets in our solar system, like Mars or some of the moons around the outer planets. So it's going to be super cool. I encourage people to check it out. We will be roasting marshmallows with a telescope pointed at the sun, so you can check that out too. Lots of fun things to do. And that will be the 25th, the 26th, and the 27th of February. So a few weeks away. But look up Death Valley National Park Dark Sky Festival for more information. Cool. Okay. Thanks, everybody, and have